Hello, my name is Mary Napolitano, and I'm the product manager for LinacView. Today, I'm going to tell you a little about the latest in LinacView. This session is being recorded, and so if you don't wish to be on a recorded session, you may leave the session now. So let's go over a bit of housekeeping before we get started. Today's webinar will be recorded. As I said previously, please enter questions at any time during the presentation in the GoToMeeting dialog box. I will answer all questions at the end of the presentation. Standard Imaging is based in Middleton, Wisconsin, and founded in 1989. At Standard Imaging, we design and manufacture a full suite of QA products. So during my presentation, I will begin with an overview of the basic workflow, then provide a bit of background on log files and how and why they're useful for patient-specific plan comparisons. In particular, the Fluence comparison is useful when alert criteria for pass-fail are based on gamma calculation criteria. I'll show some examples of specific Planfluence analysis. Just to keep in mind, though, that IMRT-QA began to ensure that the plan being delivered matched that which was planned. One can do this using second check calculations, array measurements, and log file comparisons. Each of these methods can catch different sorts of errors, and one must be aware which second checks catch which types of errors. Then I'll discuss a few recent publications comparing log file versus detector array comparisons to show what correlations exist and differences in what errors can be picked up by each. Finally, I'll review some of the new features in version 3.8 and then summarize. So here is the basic information flow for LinacView. Everything begins with the treatment planning computer and the RT plan. So the RT plan is exported from the treatment planning system to LinacView. For any plan already imported, LinacView automatically matches log files to the plan and analyzes numerous parameters. Also, the plan is exported to the Linac console. And then the plan itself has specific control points where one can determine how closely the planned versus the delivered matches. If the leaves, for example, are not traveling quickly enough, the beam may pause or the dose rate will dramatically decrease to allow the leaves to catch up. The RT plan has control points much more sparsely spaced than what the Linac log files typically provide. So with that, let's discuss log files a bit further, but I wanted to start with the basic workflow. The RT plan, of course, going to LinacView, getting delivered, and then the log files are also collected in LinacView. So there's a syncing mechanism here into LinacView, and all the analysis occurs here. So log files were initially generated, as log files are for any software, to record the delivery based on the feedback mechanism designed into the Linac. The MU, the positioning of each MLC, the gantry, collimator are all recorded. When the parameter, for whatever reason, exceeds the internal tolerance of the Linac as designed, beam off occurs. And in some cases, beam will resume once parameters are back within tolerance. We are interested in collecting, or really accessing, Linac log files during all deliveries. This is easy with Varian TrueBeam because the trajectory log file is an open access folder. Slightly more complicated is the variant Clinac because the Dynalog folder is openly accessible and you'll need to install a local tool to permanently duplicate the folder into an accessible area. The Electa log files are a bit more complex. For real-time access, we are required to use the ICOM-VX interface and then we generate our own log files from this ICOM-VX interface. This interface is suggested for use for all third-party vendors. The sampling rate, meaning the records per second for different log files, varies. And in this chart, I give a summary of the sampling rate. The older variant Clinac series samples at 20 records per second and saves Dynalog files. The variant TrueBeam samples at 50 records per second and saves trajectory log files. And Electa provides slightly different recording options. Their TRF files are generated at 25 records per second, but are not available in real time for use by external vendors. These files can be manually exported after delivery, but we're actually interested in the real-time analysis. So the other option for Electa is using the ICOM-VX interface, which was created for external vendor interface. The sampling time for these is 4 records per second. So log files can be used to make direct comparisons for multiple parameters, such as the jaw positions, carriage positions, MLC leaf positions, gantry and collimator angles, monitor unit, beam states, meaning hold on or off. Electa Linacs, for example, don't entirely beam off in most cases during delivery, but instead reduce the dose rate, table positions, and angles. As a clinical physicist, sometimes multiple small leaf misalignments or entire bank offsets can be difficult to understand and determine the clinical relevance. So in order to provide this link, one can directly calculate the delivered fluence as recorded by the Linac using the log files based upon the MLC leaf positions and the fraction of the total monitor units. So once one understands the information coming from the log files, the next step is to be able to map the log file records to the RT plan control points. The same fluence calculation can be performed based on the RT plan, such that a direct 2D fluence can be analyzed using the traditional gamma analysis between the planned and the delivered treatment. The RT plan specifies delivery based on control points. Only at these points is the configuration specified. Between the control points in the treatment plan, the leaf movement and monitor unit are not specifically defined. One typically assumes linear motion between the control points. And only at the control points are the conditions specified. This direct analysis is highly sensitive to catching errors, and I will touch briefly on some recent publications in areas later in the presentation. And as an extra step, if one is interested in investigating further, a specific plan delivery error can and one wants to look further into a specific plan delivery error, one can generate an RT plan with different numbers of control points and can map the actual delivery more closely than the delivery assumed and sent from the treatment planning system, just to go back and cross-check if there was a delivery error. So now I'm going to transition into some sample fluence comparisons from the RT plan. This is a map of the fluence from the RT plan and from the fluence from the log file. These fluence maps are created by projecting the MU-weighted segments to the isocenter plane. In this case, there's a gamma 2%, 2 millimeter criteria with a threshold of 5% specified in the calculation, and this results in a 99.7% pass rate. This value clearly exceeded the thresholds for alert or tolerance, so no action is required for this session. The next case is a 3-arc breast plan delivered using a TrueBeam, which has the trajectory log files. And similar to the previous case, the LinacView Fluence Map Comparison shows, in this case, 100% pass rate. So both of these have good results, which is not surprising. As long as you have a well-commissioned system and keep up with your machine QA. This one, again, is using the 2% 2 millimeter with a 5% cutoff. And the vast majority of plans will not generate any sort of alerts. One gets confirmation as each session is delivered, and then a summary report is generated when the treatment ends. In general, good results are not surprising as there's no setup uncertainty and no finite space detector grids. But of course, when the delivery doesn't proceed as planned, one needs to know what the alert system would look like. So here's some screenshots from a case where LinacView shows a failure. This head and neck plan with a modulation complexity score of 0.074 is a highly complex plan. The lower the MCS, the more complex the plan. This plan was delivered on a Varian Clinac, which is an older machine, so one might expect more performance issues. This particular plan had alerts for both leaf-related issues, RMS leaf, and maximum deviation alerts. As you can see here, the alert level was set to 0.7 millimeters, and the failure level was set at 1 millimeter. And you can see the RMS leaf error throughout both banks, bank A being in the olive color and bank B being in the purple. There's above the specification for a good number of leaves. And then over here, you can look on a leaf-by-leaf basis. And this is, of course, only if you want to investigate further. This is leaf pair number 10, for example. And you can see at the RT plan control points, of which the bank B leaf is beyond the leaf position deviation in millimeters. So this is beyond 1.5 millimeters. You get an alert, and a failure looks to be here at about probably 2.5. I'd have to look back to see the specifications for this one. And so we also see that there are Fluence failures. So there were alerts based both on the leaf RMS error as well as the Fluence-based error. And for the Fluence-based error, you can see here, again, we're using the 2% 2 millimeter, a cutoff of 5%. And what you can see is that the gamma pass rate was 88.5%, not surprising with the leaf movement that we're seeing with this plan. And it's shown in red here on the histogram, the 88.5%. As well, you can see the mean gamma pass rate is also a failure, so 0.495 for your mean gamma. And so while I'm showing some of the graphs from within LinacView software to illustrate the failure, one would receive alerts via the dashboard and emails upon the failure. And the software is only opened and reviewed in order to further investigate failures. And so I'm going to go ahead and just show you the dashboard real quickly. And so this is what the LinacView dashboard looks like. And prior to our session, I went ahead and sent in a plan. And you can see that for all these sessions, these are this is a 2-arc plan. So you get analysis for each arc and for each treatment session. And then you can hover, and the information that you're seeing shows that the monitor units have been analyzed, and you get 100% pass rate. The Fluence comparisons, 98.7, and then the final is the mean gamma, which is 0.183. And you can see that if you just hover, so you can keep track if you want to look, but mostly one is just depending on all these passes. But I can go ahead and send in the failing plan that we just saw, and you can see what transpires in the normal operation of the software. And so the RT plan was previously exported to LinacView, and I just sent through the log file, and that's how quickly the analysis occurred. And you can see there's a failure. We can hover over the area, or one can go ahead and see that this one had a failure for the Fluence comparison. And at the same time, normally I would get a pop-up that I had an email, but since I'm in presenter mode, that suppresses my email alerts. But if you were a physicist and you were working in your office, or if you were working from home, as many of you may be from time to time during COVID, you would immediately receive an email alert showing the same information that I hovered over. And then if you wanted to go and investigate further by opening the software, you could. So there are numerous features within the software, a mechanism that allows you to review and investigate this failure in a lot of detail, so that you can find out what's going on with your Linac. But for the most part, you'll just keep the dashboard up, and whenever you receive alerts, you can investigate further. At the end of a treatment session, you automatically close out and generate reports. So then you have a report at the end of all of the fractions being delivered that you can put in the patient chart. And so now I'll continue on with the presentation. And so you could see the dashboard, what was shown the failure, and then you can go in and investigate further for this particular plan, for example. And if you would like to see the software in a bit more detail, please just reach out to me and I'll be happy to show you all the detail available within the software. So now I wanted to kind of transition to a different topic, some recent publications with log file patient QA. And there have been a number that came out last summer and fall, and we have links to these on our website. And so investigation using log file analysis for automated patient-specific quality assurance, and then error sensitivity of log file analysis tools, and patient-specific quality assurance using machine log file analysis for stereotactic body radiation therapy. And two of the articles came out last October, and this one was a abstract at last summer's AAPM meeting. And so, just to quote from one of the publications, the log file solution is found to be, and I quote, very sensitive in detecting small delivery errors. And then the third article, I'll quote, states that log file provides a robust and reliable QA method to reduce patient-specific QA measurement, providing that a comprehensive measurement-based machine-specific QA program is in place. And these types of analysis programs provide end-to-end plan transfer as well as beam delivery checks. Physicists must always make sure that machine-specific QA is well maintained. And I'd like to go into just a little bit more detail about the results that were provided in the AAPM abstract. This particular abstract was a user, a LinacView user with an elected Unity. They delivered 66 plans and analyzed them using LinacView and measured with a commercially available detector array. 11 of the plans were incorrectly matched to check for error detection sensitivity. And so for the correct plans, the gamma 3% 3 millimeter for the detector array results range from 94.7 to 100%, which is as expected. And LinacView had similar results, 95.4 to 100%. But what I find most interesting is the gamma 3% 3 millimeter for the incorrectly matched plans. So just to give some context here, in case you're not as familiar with the Unity, each and every day the patient is set up and a new plan is created on the fly. And so you can't actually do QA prior to that day's treatment. And so each day of the treatment session, there is a new plan. And there was some concern by the individuals that investigated, how do we know if, today's plan is really the plan being delivered? And so that's where this investigation came in. So that's what I mean by incorrectly matched plan. So it was still a plan for that patient, but for a previous or upcoming day, since this was, of course, retrospective. And so with the detector array, they measured all of these incorrectly matched plans, and the gamma pass rate ranged from 3.9% to around 85%, whereas LinacView ranged from 1.2% pass rate to a little over 20% pass rate. So you can see that LinacView was much more sensitive in determining the error. And the abstract states that significant ranked correlation between log file analysis and detector-based measurements with an 86% with a p-value less than 0.01. And overall, a log file analysis can provide higher throughput due to automation, but can also provide faster patient-specific QA feedback to clinicians and physicists. So I thought that was a really interesting and informative abstract, and I'd encourage you to take a look at the two other publications that I had up on the screen. So as I promised you in the beginning, what's new with LinacView? So we released version 3.8 last month. The main feature is Halcyon support. This was challenging due to the dual layer MLC, so it took a good amount of development. And due to the workflow with the Halcyon and Ethos, a log file analysis will be very beneficial, I believe. Other improvements I would like to highlight are the addition of the mean gamma, and as well as the max gamma, both for alert criteria. Also, the ability to match specific analysis criteria to plans based on DICOM tags. This allows customized templates for different treatment type anatomical sites based on DICOM keywords read from the plan files, and then associated automatically by LinacView with a particular template using the RT plan name, label, or study description. And so this will allow the users to have different criteria for a prostate plan versus a complex head and neck plan. And in addition, if the keywords are forgotten, the software allows for manual association to templates. That part is not an automated process, but can be used when needed if keywords aren't used and you would like to customize the analysis. We included numerous other improvements, such as enhanced treatment of interrupted sessions, dashboard priority ordering, improved treatment of trajectory log files in their transition phases between beams, as well as additional improvements for Elekta and Pinnacle users. And so I wanted to just go ahead and show you a Halcyon Fluence Comparison. This is for a head and neck plan, not too complex. You can see from the MCS score, it had 2 arcs and passed all its criteria. The mean gamma was 0.066, as you can see over here, 99.5% pass rate at 2% 1 millimeter. And then you can see well, actually here I am just showing the distal and proximal bank leaf details. This is actually, I can't remember if this is a distal or proximal bank that I'm showing, but we have separate view, so you can look at each. And so you can see they're well below the alert and failure criteria. Very good delivery, but we have seen one Halcyon plan that was sent to us that does fail in the delivery versus the planned. Again, just to go over, this is the Planfluence, the delivered Fluence, and then of course the gamma comparison map. This light blue, aqua, I guess, is areas that are less than the cutoff, and then of course out in this region there's no calculation, and you can see the very low gamma values. And the histogram, you can, it's very tightly grouped. So in summary, I hope that I have convinced you that there's a wealth of information available for analysis within your log files. LinacView software maps RT plan control points to log file data. Gamma analysis of the fluence calculated from the plan and log files is used to automatically generate alerts in case of plan failure. Other machine parameters, specific alerts can be used, such as leaf RMS failure. Comprehensive analysis tools are available when needed. Also, log file analysis is more sensitive in detecting fluence-based errors compared to detector arrays. And LinacView supports variant Halcyon along with a lot of other additional new features. So at this time, thank you for your time and attention. That concludes my presentation. Please type in any questions into the dialog box and I will do my best to answer your questions. And I'll give you just a minute to do that. I don't see any questions right away. Okay, I think that concludes the presentation. If you have additional questions you think of later, don't hesitate to reach out.